Hello everyone, my name is Yangfo. I'm going to talk about our recent work on the neural discourse structure for text categorization. This is the joint work with Noah Smith. So first off, I don't think I need to emphasize the importance of the text categorization, because just think about how many applications can belongs to this category. But I do want to emphasize the challenge of this task is how we're going to represent the text into a numerical vector. Because we use machine learning model and want to the numerical vector can encode as much as information we have. So there's a well-known assumption not all the sentences are equally important or equally informative. Our contribution in this work is use the discourse structure as the inductive bias to build a distributed document representation. Okay, if this one reminds you what Noah said this morning, this is just another example of using a squash network with linguistic bias. I hope Noah convinced you why we need the linguistic knowledge as the inductive bias, but still I want to talk about why in this work we need the discourse structure. Here's the example. Which is from the Yelp review with the 2 stars. This review talks about the food. Okay, it's the restaurant review. The food is amazing. And there's a particular dish this user really like, but the service is really awful because the waiter, really just served himself and keep running to the bathroom instead of providing service. So let's think about how the prior work to select the important sentence. So I summarize the prior work as a structure like this, which I call the shallow structure. So basically, you think about all the sentences on the same level. So in this case, either you use the latent variable or using neural attention or some sparsity regularization, your model have to work really hard to find the relation between the different piece of text and the important sentence, which is really hard. Instead, we can directly use the discourse structure. So in this structure, which is the dependence structure, shows the dependence relation between different pieces of text. And also it tells you what is the relation, we call the discourse relation, or you can think about just a semantic relation between different pieces of text. And the more important, it's really straightforward to see which piece of text is more important than the other. So they have a parent-children relation. We actually used this structure in our prior work led by Batia in 2015. But in this work, we want to explore all the information on this tree structure. So let's go back to this tree structure and see what we have. We have 3 things. The first one is the whole text, of course. And the second one is the tree structure, which shows the parent-children relationship. And the third one is the semantic relation between different pieces of text. So I want to build a neural network over this structure. But the first thing I need to do is to represent each piece of text as a numerical vector. So what we did is we run the BellSTM, it's no surprise, and just concatenate the numerical vector together from the last hidden state, and use that as the numerical representation of each piece of text, which I use E as the notation. So now we're ready to build the tree structure. The first step is the basic case of this recursive procedure, which we let the numerical vector of each piece of text go through a nonlinear hyperbolic tangent function to increase the nonlinearity. The next step is we need to go one step up. So now think about the relation. Just take the right one as an example. So what we have is text A and B. What we're going to do is trying to build a representation which can represent text AB. What we have is the parent-children relation where A is the parent and B is the children node. And also we have the elaboration relation, which is the semantic relation between these 2 pieces of text. So what we actually do is we use a matrix W, which is indexed by the different discourse relation, and use that as a transformation before we combine the text A and B. Also, we have alpha here, which is a number between 0 and 1. Because the way to distinguish the parents and children is we want to downweight the children to give it like a number between 0 and 1. And we do the same thing, like one more step, we get entire representation of the whole text. So in this composition function, let's think about the top one, where we get the root node. I expand what is E, what is V. V is the representation of the text, including the children node. I expand W. There is the alpha, which identifies how we define this. Before I give you the mathematical definition, let's think about the meaning of alpha, which is the contribution from the children node to the entire of the text. And what we want is 1, this number is between 0 and 1. And 2, we don't actually want the different children nodes to compete with each other. Just think about the example in this restaurant review, where we have DEF, which is the following text, provide the further explanation why the service is awful. They're all important as a children node. It's just no reason we like them to compete each other, consider as the contribution. So that's the two property we want to maintain. And the definition of this is we use a bilinear product, and let's go through a sigmoid function. So in this way, each one will be independent with others. So to make a comparison, like what we usually have about attention mechanism, is something like this. We have the children node, again, on the right side, and the parent node on the left side. Then we normalize them. So this is the way to let the children node compete with each other, which is actually necessary in machine translation because we need to do some kind of soft alignment for the translation. But here, it is not necessary. And also, there's one numerical reason, which is going to be easier to see from this example is, if you only have one children node, the weight will be 1, which is not what we expected. Okay, so this is the model which basically have all the information I just mentioned, which is the whole text, the tree structure, and the discourse relation. So then the question is, do we really need this complicated model, or do we really need every component in this function? So to answer this question, well, I cannot give you a theoretical answer, but I can give you an empirical answer. The way we're doing this is we have some kind of ablation test. We just remove the components gradually one by one, starting from the discourse relation. We have a model variant, which we call the n-label model, which basically replace the matrix W index by the discourse relation with a single transformation matrix. And we move one more step back, remove the tree structure. So basically what we have here is the bag of sentence representation. Then we take the average. There's an extreme case is we only pick the root node of this text, which we got from the discourse structure. And this is inspired by the document summarization using the discourse structure. So now we have all the models. We want to know how this model works. The evaluation task, we select the data on purpose. With the data set range from different tasks, which you can see from the second column, from different classes, like you can see the number of the classes for each task. And also the last column will show the different size of the data. So we have 3 dimensions. All the data set is automatically parsed by the parser from my prior work with Jacob Eisenstein. Okay, let's take a look at the result. So the first result is on the app data, where we have 700 key document and 5 classes. The pattern from root node to the file node is like every time you add one component, you get an improvement. Also, the improvement is different, but the overall tendency is there, like keep increase. Compare with the state of art, we win like nearly 1 point we have an additional experiment which shows like, we make a comparison, because this, I promise you to give you like a comparison of the different attention mechanism. So this is the example on the YAP data. The reason we choose the YAP data is because YAP data have enough document, like 700 key document. So there's okay. So we just eliminates the factor like, okay, what if we don't have enough data? So that's the reason we picked the YAP review. So the experiment results show if we use the normalized one, if you use the one used to let them compete with each other, we actually get a performance drop 1.5%. Now, if we compare how much we win over the previous state of art, this is pretty much a big drop. So we should ask, actually, this is empirical results about our linguistic intuition. Well, another experiment I could show you is the result I'm going to show you is the smaller one, which the pattern is slightly different. Now the best model is the unlabeled model. So this is actually not a surprise, because consider the size of the data and consider the size of the model. The unlabeled model is more than 10 times smaller than the full model. As the bigger one, the bigger model, the full model is really easy to get overfitted. And you can see the similar pattern on two other data sets, which is congressional flow debate and the movie review data. One more result I want to show is the congressional bill corpus. So this one is interesting. None of our model is better than the state of the art. So which basically shows like the discourse structure doesn't help at all. But to me, this is not a surprise. I mean, we shouldn't hope like the model training on the Wall Street Journal, which is the RSD corpus, can give you a reasonable structure for the document like this. I even did some cleanup to make this document look better, but still you can see the difference. I mean, the whole point here is, if you consider use the discourse parser for the application, and no assumption is better than the wrong assumption. Okay, so what do we got from this work? First of all, we proved like from the 4 tasks over 5, we proved like automatically discourse parse the result is helpful for the text categorization. And there's an additional result, which is not here, but in the paper shows if you can increase the performance of the discourse parser, you can get even better performance on the text categorization. So this is the motivation to keep us working on discourse parsing. But there's another one, which is showed by the result on the congressional bill, is we should pay our attention to to the data sets from our other genre, like the bill corpus, like the medical domain, something like that. Okay, that's what I'm going to talk about today. Thank you.
We have plenty of time for questions. So if you have questions, please come to the microphone.
Hello, thanks for the talk. I enjoy it. I just have one question. Have you measured the effectiveness of a wrong distinguished parent and children relationship that may affect your model? Because I think most of the discourse parser we have these days only have a 70% correctness rate of finding the correct parent. Mm-hmm. Would that the 30% of error of parent cause a huge effect to your model because you treat these parents as relatively more important one in your recursive net? Thanks.
We don't have a quantitative evaluation, but we do have like some example in the paper, which shows like if the model gets the structure wrong, they basically confuse the model to give you a right answer. Like, okay. You know.
Okay, thanks for telling. No.
Any other questions?
So I'm not sure if this is a question or a suggestion. It depends on whether it's something you're already thinking about. There's a bunch of work on citation analysis in academic papers, which is trying to figure out which citations are important to the paper and which are being mentioned in passing, among other things. There's finer grained distinctions that you could also make, but that work is also generally making use of rhetorical structure to figure out where the mentions fall in the flow of the argument. Have you thought at all about the relation of these methods to those? Would they help on your task, or would your methods help on that task?
Well, this is definitely a suggestion. But I think intuitively, I'm thinking like the discourse structure, if you can figure out the relation, like, okay, for example, if there is in the paper, if they mention about, okay, we propose a new method compared to something else, and if the discourse model can figure out the relation of these two pieces of text, it's definitely help to figure out, okay, what's the point of this paper and which one is more important than the other. But again, I think we still need some kind of annotation on this on the paper stuff like that.
Yeah, so I think people have used RST in the citation analysis stuff. So there is annotation there as well.
Big data set or something like that?
I don't know. So I don't know this.
I'll talk to you later.
For people who are interested in following up on this, Simon Teufel, T-E-U-F-E-L, was one of the more prominent people in ACL working on this, and some others as well, I think.
It's good, and thank you. This is definitely a good suggestion.
Hi, thank you for the talk.
Thank you.
I've been seeing sort of discourse structure work in talks for many years now, and often the theme is exactly what you had in your slide, like, all right, you have a good model, but then you add discourse structure.
No, I shouldn't do that.
That wasn't me. And you think it's going to work, but it works a little bit over what you already have, or it sort of flatlines. And it kind of got me thinking, listening to your talk, it's like, this is the random question of the day. Do you think RST is the right representation to use? Like, even if you had a perfect RST parser, would that really solve, like, how much would it solve?
Well, I think, well, I don't think I'm qualified to answer this question whether the RST tree is, is a reasonable one. But there's a argumentation between the different discourse structure. I guess my work is trying to show whatever, I'm working on the RST tree bank and also the Penn discourse tree bank in my prior work. So I guess my work is trying to show that discourse information does help. Like, for example, in this work, none of the data set we test is on none of the data set we test is on the Wall Street Journal. It's some sort of cross domain, but still the discourse parser helps. So it's kind of like, I wouldn't say it's a strong evidence, but I do think, it's promising. Thank you.
Thank you for the great talk.
Thank you.
And I know that you have been working on RST parsing for a long time, and I really respect that. And so did you use off-the-shelf approach for extracting the relations of these texts? In that case, how did you deal with the emojis or ungrammatical text from Yelp reviews or movie reviews? And also, did you get a chance to evaluate your model, the discourse relation prediction of your model?
We use the discourse parser from my prior work, and we didn't do, other than the pre-processing, remove the real word something, which is mentioned in the paper. Other than that, I didn't do anything to normalize the word or something like that. Okay. So, well, that's a good point. I mean, if you have a clean text, the model will do better. The discourse parser will do better. But here, there's a lot of data set. There's no way we can just, change them one by one.
And about the Congression bill text, you said that discourse relation parsing in that type of text would be really hard. Then what is the most difficult thing?
So first of all, the vocabulary size, I guess, is quite different. Okay. That's one. Second one, they have a different discourse structure. I'm not sure what is the discourse structure of this one, but think about the discourse structure in the Wall Street Journal. Usually you have a beginning sentence talking about something overall. Then you start to elaborate what you have as the beginning. So it's kind of like you have a summary, then you have elaborate what you're going to talk about. But this is not the case here, the build corpus. So this, I think, is two reasons.
Thank you.
Okay, let's thank the speaker again.
Thank you.